Okay, hi guys, how's it going? So today I want to talk a little bit about one of the next topics, which is light. And in order to understand light, um, we need to understand a few things about how light works. So we have the lab number 214, and you should be doing that this week. And that lab has to do with light. Now, when we talk about light, the way we think about it is in terms of something called a light ray. And a light ray is like sort of one um, straight line of light or one path that light takes from a source, some um, receiver, which could be your eye. So um, let's look at the first example. Suppose that you have a mirror on the ground. And let's say you have a flashlight over here, and there's a flashlight here, and it makes light rays. And these light rays, they come, this is a light ray, it should be straight, and it hits the mirror. So a lot of light comes from the flashlight, and it hits the mirror. And the question is, how does this light behave when it hits the mirror? And this is one light ray, that's another light ray. This is a flashlight. So the way we think about this is we want to measure the angle at which the, the light ray hits the mirror, okay? So usually what we do is we draw what's called a normal line. And a normal line is just a reference line which allows us to calculate angles. So this line here is called a normal line, and it's just a line that allows us to calculate angles between what's called the incident ray. This is the incident ray, and I'm going to draw a little arrow to tell you that these rays, they're coming from the flashlight and they're going towards the mirror. So I'm just giving an arrow to indicate the direction of each light ray. Now the way you measure the angle is you look at this angle, and you can use a protractor, and this is called theta incident, or I for incident. And this here are called incident rays because they're coming towards the mirror, but they haven't hit the mirror yet. Okay, so these are the incident light rays. And of course, once the light ray hits the mirror, usually what happens is it will be reflected. Okay, this is called a reflected light ray. It bounces off the mirror. And there's something called the law of reflection. Law of reflection. The law of reflection says that, sorry, it's a little bit slow to write with my mouse. The law of reflection says the angle of the reflected, this is the reflected light ray, the angle of the reflected light ray is equal to the angle of the incident light ray. So what does that mean? That means if you measure this angle from the normal to the beam, to the light ray, theta reflected, theta I is going to be equal. So this is theta I is equal to theta R. And what we do in part one of this week's lab is we'll measure these two angles and see if this is true, okay? Remember, this is called the normal line here. And it's just a reference so we can measure our angles, okay? So that's part one of the lab. Now let's look at part two. For part two, it's a little bit more complicated. What we want to do in part two is we want to see what happens when light rays hit glass. Okay, so let's say this is air here, and there's a piece of glass over here, and over here, this area is all made of glass. Okay? This is glass. Okay? So now when we have our flashlight over, let's say we have a flashlight here, the flashlight is going to send light rays towards, from the air, we point it down towards the glass is sitting there. The light ray will hit the glass, and when it hits the glass, the light ray will do two things. One thing is that there will be what's called a reflected ray. Just like before, there's going to be a reflected ray. So just like before, we have the normal line. Okay, this is the normal line. Just drawing the normal line all the way through. And the normal line is just, perpendicular to the surface there. So this will be the reflected light ray from the surface of the glass. If you ever look at glass, sometimes you can see your reflection, but you can also see through the mirror, right? Sorry, see through the glass. So this is the incident light ray from the flashlight. Incident. Now, but there's one more thing that happens, and what happens is, I'm just going to erase this so you can see, this area is still glass over here. You know what I'm going to do is I'm going to try to make it clear that this area is glass. I'm going to see if I can fill it in with a different color. Let me see. Can I make this a different color? Well, never mind that. So over here, this glass, this whole area is glass down here. Well, I don't know how to do that, but just keep in mind that that area is glass. Let's go back to black color. So down here is glass, and up here is air. Now, when the light ray hits the glass, it's going to send one reflected light ray, but there's also going to be what's called a transmitted light ray. And that light ray will go through the glass. Okay, so this is called the transmitted. This is the transmitted light ray. So some of the light is reflected and some of the light is transmitted. And when the light is transmitted, there's an angle, what's called an angle of transmission. This angle is measured like this. This is called theta t. Some people use different letters than t, but I'll use theta t. So now we have three angles for this situation. The incident angle, angle of incidence, the angle of reflection, theta r, and what's called the angle of transmission, theta t. Now, other textbooks sometimes call this is called refraction instead of transmission. The other word that they use is refraction. But all that refraction means is that the light is transmitted. And what you will find is that when the incident light ray hits the glass, which is heavier than air, the light ray will bend this way. It will tend to go closer towards the normal line, okay, because glass is more dense. And the way that this is understood is in terms of something called the index of refraction. Index of refraction, N. That's called N. And the index of refraction is equal to the speed of light in air divided by the speed of light in whatever medium, for example, glass. For example, N for glass is equal to 1.5 for glass. Because what happens is when light hits the glass, it slows down. So the speed of the light going through the glass is going to be less than the speed of the light through the air. C is the speed of light through air. So you can see that the light is traveling faster in air, but because glass is more dense, it will slow down. And this index of refraction is going to be important in telling you how the light ray will bend towards the normal. And the equation that we use is called Snell's law. Snell's law tells us how much the refracted or transmitted ray will bend towards the normal in the situation where you're going from a less dense air. Air is less dense compared to glass. In this situation, the light ray will bend towards the normal. This theta t is going to be less than theta I in this situation. The glass is more dense. Now, if it was the reverse situation, if you were traveling from light, if the light started in the glass, you had a flashlight inside the glass and you point towards the air, then it will bend away from the normal. So basically, if the light ray was going this way, then it would actually go farther away from the normal line. So you can just kind of put it in reverse, right? So if you start the light over here, it will do the exact same thing, but it will go in reverse. In this case, it will bend more away. Okay, but it depends which way you're shining the light. Are you shining the light from over here, or you're shining the light from over here? You're going to get the exact same profile, but it will still give the same exact shape. It's just have a different direction. You can go either way with shining the light. Okay. Snell's law says that n1 sine theta incident is equal to n2 times sine of the transmitted angle, theta t. So basically, so for this case, for n1, n1 is air. So for air, n1 equals air, and air. So that's equal to just speed of light over speed of light. It's just equal to 1. So it'd be 1 times sine theta incident equals n2. n2, this is glass over here. Glass has an index of refraction of 1.5. So you multiply 1.5 times sine of theta transmitted, okay? And then you can solve for, let's see, theta transmitted. Basically, if you have, um, 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 you know, you can solve for theta transmitted. You don't really need to do this, but you could solve it as sine, um, it will be the inverse sine of this, right? Inverse sine of sine theta over 1.5, right? That's how you could solve for the transmitted angle. Okay. So that's kind of the theory. There's one more thing. That's how you solve part 2 of the lab. And then for part 3, I'm going to make a new slide here. For part 3, what you're doing is you're doing something called total internal reflection. And total internal reflection means that, let's say you have some glass here. This is glass. So let's say you shine a light this way. Well, when you do that, there's usually a reflected and also a transmitted. So this is the incident light ray, this is the reflected light ray, and this is air over here, and this is the transmitted light ray. Total internal reflection refers to, it's also called TIT, or total internal reflection. It's a phenomena, let's call it TIT, whereby this phenomena is a phenomena whereby when you shine the light into the glass, all of the light, when it hits the boundary, so over here, this is a piece of glass. And when the light ray hits the boundary, total internal reflection means that when it hits this boundary, none of the light escapes. All of the light stays inside the glass. So this is the incident light ray, and this is the reflected. And there is a certain critical angle. So this is the normal. Let me just erase that. Let me draw the normal here. Here's the normal line. There's a certain critical angle, a critical angle of incidence such that no light escapes this surface, this boundary between air and glass. So this line here represents a boundary between glass and air. Over here is air. At a certain incident angle, theta, there's a certain critical angle, theta I. Critical, if theta I is more than this critical angle, no light will escape. No light will be transmitted into the air. Okay? As long as theta is less, if the incident angle is less than theta I critical, there is transmission into the air. The light ray, there is a transmission. But if it's the other case where theta I is more than or equal to the critical angle, there will be no transmitted ray. Okay? So that's the two cases. Okay? So what you do in the lab is you want to sort of test out these ideas. You're going to basically take your light ray and shine it, and for part one, you take your protractor and you're going to measure these two angles. So this angle is 0, looks like 36 degrees. This angle, okay, maybe I didn't do it quite right. Let's try to get this. Here, this is 35. 36, this is 35, wait, no, 30, 32.5, okay, wait, let me just get the scale. So this is 10, 20, 30, 40, 50, so 46 degrees over here and 46 degrees. So what you would do at this point in part one is you'd write down theta I is equal to 46 degrees and theta R is 46 degrees. So we verified part one. If you go back to part one, we want to verify that these two angles are equal, and we found that indeed theta I was 46 degrees and theta R was also 46 degrees. And it just wants you to check that for part one of the lab. So you do that a couple times. Then for part two, what you're doing in part two is you need to measure different angles theta I, you want to measure different angles theta T. So I don't know if it calls it theta T or theta refraction, something else. This is the refraction over here. So for example, if I set this to 30 degrees, this is theta I is 30, theta T is clearly 10, 20, it's about 18 degrees. So then I would go over to my sheet and I would write, theta I, this angle is 30 degrees, And then theta t, I found that's 18 degrees over here. That's the transmitted or refracted angle. Okay, so you just go back to the experiment, and then you rotate this by 10 degrees, and now theta I is 40, and theta t is 10, 20, 24 degrees. So you keep doing that, and what you should see is that this law will hold true. If you plot sine theta I versus sine theta t, the slope should be 1.5. So that's what you want to plot. And that should give you the index of refraction. And then for part 3 of the lab, you're going to try to see if you can find total internal reflection. Remember, I said total internal reflection is when there's a critical angle such that there is no reflected light ray. So if we keep rotating, we see that at around, see, 40, 44, 45, 43 degrees, now there's no light ray escaping into the air. So if theta incident is more than 43 degrees, there's no now there is refraction, there is transmission. But if the critical angle is too big, that's right here, right around here, you get what's called total internal reflection. And this is the critical angle, which is about 43 degrees. So you're going to write down 43 degrees as your critical angle, and then you're done with part 3. Okay, thank you. That's the end of this lab lesson. Let me know if there's any questions.